Welcome to the video notes on forces. What follows is going to be your notes dealing with forces. I would recommend that you also review your notes from our vector unit as well as our notes from Newton's laws. Those will be very helpful for you during this particular video. So let's go ahead and get started. First, we're going to talk about equilibrium forces. Those come in different forms, particularly the concurrent forces, which you have two or more forces acting on the same point at the same time. You have a resultant force in which you have the concurrent forces acting together. Now, when all the external forces are acting on an object and they happen to cancel each other out, in other words, equal and opposite magnitude, you end up with a net force equal to zero, and then you say that that object is in a state of what's called equilibrium because all the forces equal each other out. So in a state of equilibrium, the object is either at rest or it moves with constant velocity. This is Newton's first law. So this is sort of an application of the Newton's laws that we learned earlier in the semester. Now, if you have concurrent forces acting on the object, the single force that puts the object into equilibrium is the equilibrium force. You could have four forces acting on it, and if that 1/5 force puts all the others in equilibrium, no matter where it's positioned, no matter what its magnitude or the direction it's pointing in, if it puts all those other, if it balances out all those other force vectors and puts the object into equilibrium, then that force will be the equilibrium force. So what is this equilibrium force? Well, it's the force that is equal in magnitude but opposite direction of the resultant force vector. And if you don't remember what resultant is, once again, go back, look at your old vector notes and review that. The resultant, in other words, an example would be if the resultant is 45 newtons to the east, your equilibrium would be 45 newtons to the west. So again, equal in magnitude but opposite direction, which is Newton's third law. Now, we've all familiar with friction. We use it. We use the term a lot, and it's something that opposes motion. And this only occurs when objects are in direct contact with each other. It also acts parallel to the surface that the objects are moving on, and it acts in the opposite direction of the motion. So let's say that the object is moving east, friction will be pointing west. We don't really know the exact causes of friction. We do have an idea that the surfaces of objects are not entirely smooth because we're zoomed out so far from them, because we have a huge, we don't get to see the surfaces of these objects. But if you zoom into these surfaces, including the surface of your table or anything like that, they're actually rough because they have all these molecules on them. And there is a current idea or theory that as objects touch, they temporarily become connected to each other, and so that's what's causing the friction. We don't know that. That's just some speculation at the moment. There's some evidence that leads us to believe so, but nonetheless, we just don't have enough to really say one way or the other as to what causes it. There are two types that we do know of, though. One type is static, and that opposes the start of motion. So that's if you have an object at rest, static friction is keeping it there, so it's not moving initially. Then you also have kinetic friction, and this is the force experienced when an object is moving against another object or surface. Kinetic friction is probably the one that you think of most of the time when you think of friction. It is important to note, however, that your force of static friction is always going to be greater than your force of kinetic friction. Now, friction depends on several things. The nature of the two surfaces, how smooth the surface is, and the normal force, which is a surface force that results from two objects in contact. It does not, though, depend on the area that is in contact. So even though it depends on the nature of the surface, the two surfaces, the smoothness of the surface, and the magnitude of the normal force, it will not depend on the area of the surface that is in contact. There's something called the coefficient of friction, and that is just the ratio of the force of friction to the normal force from the surfaces pushing together. Now, the normal force on a horizontal surface and keep that in mind, the horizontal surface is equal to the weight. It is a constant, so if the weight increases, so does the force of friction. The symbol is the Greek letter mu. This is not a U, it's called mu, and it's actually the Greek letter M. But it is called mu. It has no unit because it's a ratio between two forces, so the forces would cancel out. And the equation is that mu equals the force of friction divided by the normal force. So let's talk about friction as it relates to horizontal motion. So there are two scenarios for horizontal motion and the effects of friction. The first is if the object moves with constant velocity. If objects are moving with constant velocity, that means the forces acting on it are balanced. You have a situation with balanced forces. And Newton's first law is going to apply. The second scenario is when you have an object that's accelerating. In this case, you have unbalanced forces acting, and Newton's second law will apply. And if you can't remember what Newton's laws are, just go back and review your Newton's law notes for which law is which, although you should remember, especially from your projects. So let's look at the first scenario, which is friction and constant velocity. What you're seeing here is a free body diagram. And free body diagrams show all the forces acting on an object. So you'll represent the object by a dot, and then you'll draw all the forces acting on it. In this case, you see that we've drawn the weight, which is due to the force of gravity, pointing down. We have our force of friction to the left, our applied force to the right, and then our normal force is pointing up. And so if you notice over here, I have the equations listed based on this diagram. I have the normal force is balanced with the weight, so the normal force is equal to the weight in this case. The weight is equal to mass times the acceleration due to gravity. So that's what mg is. It's the mass of the object times the acceleration due to gravity, which is 9.8. The applied force in this case is equal to the friction force. And the net force is going to be the applied force plus the frictional force. But since the frictional force is negative, the net force is going to be 0, and the box is going to be moving at a constant velocity, which is Newton's first law, that objects in motion will stay in motion, or objects at rest will stay at rest unless acted upon by unbalanced forces. These forces are balanced, so this object will continue moving at a constant velocity. To find the coefficient of friction, we'll take the friction force and we'll divide it by the normal force. You could also take the applied force and divide it by the weight, in this case of constant velocity. So let's now look at the acceleration model or scenario. So in this case, we have the normal force is equal to the weight, again, and the weight is mass times acceleration due to gravity. Now, in this case, though, the applied force is going to be greater than the force of friction. So if we go back to our net force is equal to the applied force plus the friction force, we have friction being negative, and so the net force is not 0. So we need to set our net force equal to mass times acceleration due to Newton's second law, so that we find out with what acceleration the object will accelerate at. And we can use mass times acceleration equals the applied force plus the frictional force. And then you can either find the mass of the object or you can find the acceleration of the object depending on what information you're given. So that's the basics of how to set these draw these problems and set them up. The last thing I want to talk about right now is vertical motion and the net force involving vertical motion. Now, there are only two forces involved in vertical motion. You have weight, which points downward, and you have an applied force, which would point upward. The normal force is not involved because the normal force is a force perpendicular to a surface, and since we're talking about vertical motion, assuming that it's in the air, there is no normal force, or assuming it's being suspended by a rope or something like that. But there's no normal force with vertical motion. We are also going to assume that air resistance is not involved. And so there are also no horizontal forces involved. So make sure that you're familiar with these assumptions. Now, here's a free body diagram of vertical motion. So our net force is equal to our applied force plus our weight. So if we could also set that equal to mass times acceleration, since the net force does equal mass times acceleration due to Newton's second law. So we end up with mass times acceleration equals your applied force plus your weight. So these are so we've looked at situations in which we have horizontal motion and vertical motion, and how to draw diagrams of them and set them up. In the next video, we're going to talk about forces at incline on objects at an incline. So if you have any questions, don't hesitate to ask your teachers. We're more than happy to help you through this. We'll also do plenty of practice with this.